In a previous video, I covered the left and the right Riemann sums. And if you haven't watched that video, or at least been in class when we went over that, make sure you watch that first, because this is going to assume you have some idea what's going on with Riemann sums. I wanted to address first a little bit about why we even bother with area under the curve. A really easy example is that if our curve represents the velocity of an object, then the area underneath that curve tells you the total distance traveled. So there are some very practical applications for finding the area under a curve. Pretty much any rate, if your equation is a rate, then the area underneath adds up the total, is the idea. So let's look at this one. We have y equals negative x squared plus 5 from 0 to 2 on 5 subintervals. This is actually the exact same example I started with on the left and right Riemann sum as well. But I did that on purpose because I wanted you to be able to kind of compare. I'm going to fix this. This is a little rough. Whoops. Alright, that's a little bit better. So there's y equals negative x squared plus 5. And we're going to use, instead of either the left endpoint or the right endpoint, we're going to use the midpoints. So for example, we have 1, 2, 3, 4, 5 subintervals here. Remember, we do not care what happens beyond 2. Doesn't matter. And we need to find the midpoints. So the midpoint between 0 and 0.4 is 0.2. Now, if you prefer to use fractions, feel free. You can do this either way. But what I have to do is take that midpoint, follow it up, and draw a rectangle of that height. So this time, my width is going to stay the same the whole way through. I have equal subintervals, and they're all 2/5. So they're still 2/5 wide because it's 0 to 0.4, 0.4 to 0.8. You can use 0.4 if you'd rather. Doesn't matter. And my first height is going to be whatever I get when I plug in 0.2. So we'll come back and we'll do that later. Okay, now between 0.4 and 0.8 would be 0.6. So I follow that up, and I draw a rectangle right there at that height. And then between 0.8 and 1.2 is 1, and if I follow that up, I draw a rectangle right at that height. Sorry, that one was way off. And then 1.2 and 1.4, I draw a rectangle at that height. So let's go ahead and fill in these other ones, f of 1, f of 1.4, and then finally between 1.6 and 2 is 1.8, and we add that as well. So those are the ones I'm going to add up, and if you notice, midpoint is going to generally be more accurate than the left and the right sums. The reason is it both overestimates and underestimates. Now it's still not going to be perfect unless you got a straight line, but anytime you're dealing with a curve, which is the reason we're doing this in the first place, anytime you're dealing with a curve, the amount that it overestimates is not going to be equal to the amount it underestimates. But they're going to balance each other out better than just the left sum or the right sum. So midpoint does tend to be better than the left sum and the right sum. So let's plug these in now. I've got a calculator here we can use. So one thing you can do to make this real quick, our equation is negative x squared plus 5. So if I go to y equals, I can clear this out and plug in negative x squared plus 5, and then go to my table. And I can just plug these points in real quickly. 0.2, 0.6, 1, 1.4, and 1.8. So there I get my values, 4.96, 4.64, and so on. So now I can just add those all together, multiply by 2/5, and I'll have my answer. So 2/5 times parentheses 4.96 plus 4.64 plus 4 plus 3.04 plus 1.76. And we get 7.36, which if you remember the answers from when we did left and right, we got 8.08 and 6.48. This is in between the two of them. It's not the middle, like the exact middle or the average, but it is in between the two of them. And that's one way you know you probably are on the right track. is that it's somewhere in between your left and your right. So that's how you handle the midpoint. Let's do one more with midpoint. So again, this is the same second example as from yesterday. We're going from 0 to 2, 4 subintervals, so each one is 1/2 wide. So my middle points, or midpoints, can be 1/4, 3/4, 5/4, and 7/4. You can see how on the previous one I used decimals, this one I used fractions. That's completely your prerogative. So as I draw these, I have a rectangle here, 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 and here. But you've got to use the heights that you get from your midpoints. So again, equal subintervals, so 1/2 times, and then I plug 1/4 in, so 1/4 squared plus 3/4 squared plus 5/4 squared plus 7/4 squared. I'm going to plug all those in and see what I get. So 1/2 times 1/4 squared plus 3/4 squared plus 5/4 squared plus 7/4 squared. And you get 2.625 as your answer. Okay, now this may feel like it's a whole lot quicker than left and right. It's really just that we're only doing one of them. Left and right, we are always doing them together. So left individually and right individually are about the same as this. It's just that we're only doing one at a time right now. So you may be asking, well, if midpoint's almost always better, why do we even bother with left and right? And so I want to give you some idea of why that is. So let's look at this last example for midpoint, where it says approximate the area from 10 to 90 using 4 equal subintervals. Okay, so I want you to look at this table for a minute. Let's just assume this represents some real-world data. If this is the only data we have, and we want to use a midpoint sum, then 4 subintervals is the best we can do. So here's what I mean. We can't just say, oh, well, I want to use the interval 10 to 20. Well, the midpoint of 10 to 20 is 15, but we don't have any information about what happened at 15. We only have it for 10 and 20. So we have to use fewer subintervals because we are doing midpoint with data instead of with an equation. With an equation, yeah, midpoint's pretty much always better. But with data, when we just have data points, it's not necessarily any better. Because if we were doing left or right Riemann sum, we could do 8 subintervals, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70, 70 to 80, 80 to 90. 8 subintervals. But because we're using midpoint, we have to only use 4 subintervals. And that means we're less accurate because we have fewer subintervals, or could be less accurate, I should say. We may not be, but we may be less accurate because of fewer subintervals. So since we're going from 10 to 90, that's a distance of 80. Splitting it up 4 ways, that's going to be 20. So the width of each one is 20, and that is the same each time. So our intervals are going to be from 10 to 30, 30 to 50, 50 to 70, and 70 to 90. So the midpoints I'm going to use are 20, 40, 60, and 80. Those are the midpoints between my intervals, and their heights are 11, 49, 17, and 25. And when I add all that together and multiply by 20, I believe you get 2040.